we're very happy to have Vincent here. And yes, please give the stage.
Yes, thank you for the invitation. So I'm going to present a part of the work I've done during my PhD. And actually, this is a joint work with Bénédicte Haas at Université Sorbonne Paris Nord. So I will present the so-called frozen Erdős-Rényi model and explain its relation with a uniform random forest. And this will be the occasion of studying this uniform random forest using a well-chosen condition random walk. So let us start with the definition of the frozen Erdős-Rényi model, which is a modification of the classical Erdős-Rényi random graph. So I'm just going to start with some definition of the classical model. And I'm going to present a dynamical version of this Erdős-Rényi model, which is maybe not the most commonly used, but I prefer it since it enables us to couple the frozen and standard Erdős-Rényi models. So how do we do this? We just start with isolated vertices. So here, for example, we have 12 isolated vertices. And at each time, we add one edge uniformly and randomly among all possible edges. So here we add one edge, second one, and at the end, here we have an Erdős-Rényi graph with 12 vertices and 9 edges. Okay, so this model was mostly studied by Erdős-Rényi in the 60s, in the 20th century. And they were interested in the asymptotic behavior of this random graph model as its number of vertices and edges go to infinity. And one question that interested them was the behavior of the largest component in the graph. And so in a seminal paper in the end of the 50s, they proved one famous theorem of phase transition for the size of the largest component in this graph. And more precisely, they proved that the largest component exhibits a phase transition, meaning that if the number of edges in the graph is less than the half of the number of vertices, the size of the largest component is small in front of the whole size of the system. That is, the size of the largest component we scale by n converges to 0.
Can I ask what do you mean by large that component with lots of lines attached?
Sorry, the largest component in my mind is the component which has the more vertices.
Okay. Yeah.
Okay. Yes. And then past this critical point at 1/2, you have the emergence of a unique giant component, which size is comparable to the whole system size. That is, if you rescale the size of the largest component by m, this converges to some positive quantity. And this is a unique giant component in the sense that all the other components are small and they are size log n. Okay, and more precisely, what can we say about the size of this largest component? Its limit is, we can verify that it's the unique solution to this equation. And we can also check that the function given by this limit is continuous. Okay, so this is what we call a fluid limit result, in the sense of we get a convergence after rescaling by the size of the whole system, and this converges to some deterministic and continuous process. Okay, so the idea of this presentation will try to give fluid limit results, but not for the Erdős-Rényi model, but for the frozen Erdős-Rényi model. Okay, so because this phase transition result motivated many researchers, and it's motivated researchers to introduce random graph model that prevent the formation of a unique giant component. Okay, so in this direction, I just put two examples. For example, there is the frozen percolation model which was introduced by David Aldous, and where connected components that contain more than a threshold function alpha n cannot merge, and so there will never be a giant component in the graph. And another example in this direction is the forest fire model, where connected components have the possibility to burn, and the probability for a connected component to burn is proportional to its number of vertices, so that the largest component in the graph will have more probability to burn, and it will again prevent the formation of giant components. Okay, so we aim to introduce a model which is in the same direction of these two models, but we follow a different way. And the idea to do this, we want just.
So you are trying to do this because so you want to stay just in one phase.
What?
Is that why do you want to try to do this? Why are you trying to get rid of this? I mean, you're going to stay just in one phase in this way, right?
Yeah.
Okay.
But we want to do fine. I have no really motivations to do this except the model in itself.
Okay.
But it is just to see that there were people which did something like that, and our model is actually in the same direction, even if it doesn't take the same way.
Okay, then you're going to see non-phase transition, right?
Yes, actually, we are going to see phase transition, but for, let's say, analogous quantities of the graph. Okay. Not for the largest component, but for some quantity which will play the role of the largest component in some sense.
I see.
Okay, thank you. And so here the idea is to prevent the formation of the giant components by forbidding the creation of multicyclic components. So in our graph, we will only contain trees with no cycles and unicyclic components with only one cycle. The idea is that in the Erdős-Rényi random graph, in the classical model, the giant component is the only component which contains more than one cycle, and the other components are either trees or unicyclic components. Okay, so we believe that it has an impact on the formation of this giant component. Okay, and how we do this? We fix a parameter p between 0 and 1. And like before, we start with isolated vertices. And again, we choose edges uniformly and independently, but we follow some rules to decide if we add the edge or not to the graph. And the rules are the following. So if the edge tries to connect two trees, we simply add the edge to the graph. But if this addition creates a cycle in the component, so this produces a unicyclic component with one cycle, we decide that this component is frozen, and we are going to slow down the evolution of this frozen component. Okay, so for example, if the edge connects two frozen components, we simply discard the edge and we do not add it to the graph. And finally, if the edge connects a tree with a unicyclic component, we add the edge with probability p and we discard it otherwise. And if we add the edge, the whole new larger unicyclic component is frozen. Okay, so for example, if p is equal to 0, you will never connect a tree with a unicyclic component. So in the case when p is 0, the evolution of the unicyclic components is completely stopped as soon as the cycle appears. And in the opposite case, when p is 1, what you have is that the only discarded edges are the one connecting frozen component. Okay, so that is all for the definition of the frozen Erdős-Rényi model. And now we are going to try to present some fluid limit result, but not for the size of the largest component. And we are going to study actually the number of frozen vertices.
So for now, can you already see that there is no giant component or not yet?
Actually, we will have some giant components, but not a unique one.
Okay.
Okay, this is the difference, but we are going to have a set of giant components. I'm not gonna talk really about it today, but this is what we actually believe that it will happen. Okay. And so what we will study is the total number of frozen vertices, okay, which will play the role of the largest component in the classical model. And so what we proved with Benedict is that we have a fluid limit result for this quantity. So in the same regime that I presented before for the classical Erdős-Rényi, if you rescale the number of frozen vertices by n, this converges to some deterministic function again, which is 0 before time 1/2. So this is the same thing as in the classical Erdős-Rényi case, and then which verifies some differential equation, which is a bit obscure for now, but I will try to explain why these differential equations appears in the limit. And just to mention, here we restrict ourselves in the case where p is positive. Okay, we forget for now the case p is 0, and we will only talk about the case where p is positive. Okay, so just to illustrate, what we have is that before time 1/2, we have functions that are 0, and then they are strictly positive. Okay, so here, for example, you have the fluid limits in blue in the case where p is 1, and the fluid limit in red where in the case where p is 1/2. And the second,
make a solution of the differential equation.
Yeah, I represented the solutions of the differential equation before.
So it's not numerical, it's just an analytic solution.
Yeah, it's not just an analytic solution. And just to mention, already one part of the results was already known before. It is what we call subcritical part. So it was known thanks to results of Alice Ponta and Nicolas Curien, and thanks to my results also, that at the critical point, the total number of frozen vertices is of order n to the 2/3. So actually, this whole point before time 1/2 was already known, and we are just going to focus on the so-called supercritical regime today, and try to see why we have these curves in the limit. And just before giving some ideas of the proof and give the relation with random forest, I'm just going to give an application of this result, which is actually another fluid limit results, but for another quantity of the graph, which are the number of trees of any given size in your graph. What we get as a corollary is that we have a theorem, which is again a bit obscure first. So we have a fluid limit result for the sequence of number of trees of any given size to again some deterministic functions in the limit, which are completely explicit. But maybe more interesting than their concrete expressions, the interesting fact about these functions is that they verifies some system of differential equations. And this implies that the frozen Erdős-Rényi model, when you made P varies, is an interpolation of some noun coagulation equations, namely the Smoluchowski equation, which is this equation in the case when P is 0, and which appears in several random graph models, such as the forest fire model. And it interpolates this equation with the Flory's equation, which is the case when P is 1, and which appears, for example, in the classical Erdős-Rényi model. So this enables to to place the frozen Erdős-Rényi maybe in a more broad context of a random graph and with this relation with a coagulation equation.
This n now, is it the same as the frozen component or is it different, the capital N?
No, the capital N is a notation for the number of trees of fixed size.
Okay. Okay, so it's a different thing.
Yeah. Maybe the notation is not.
Yeah, I was just trying to follow.
Sorry.
No problem.
Okay, so this was an application. So now the idea of the talk is to try to give a proof of the previous fluid limit result or ideas of proof.
Yeah, so now, so there is T, it's not equal 1/2, it's not anymore the phase transition, right? Now it's just 0 that you have a phase transition.
Yeah, actually, what you have is that the functions in this limit are smooth on R plus.
Mm-hmm.
But the interesting thing is that they depend on the function which appears. So there is still a phase transition when you look at their sum actually, and you see the phase transition at 1/2 when you look at their sum.
Okay. I see, because the function would be different because it's depending on GP.
Yeah, exactly.
I see. Thanks.
Okay, so how can we try to prove the fluid limit results for the quantity Gn? Actually, the first trick is not only consider the number of frozen vertices, but the couple Gn dn, where d represents the number of discarded edges. Okay, remember there are some edges that are discarded, and we can just count them and remind this quantity. Okay, so we want to prove another fluid limit result for this couple. So we scale this couple by n, and we want to prove that after rescaling, this converges to a couple of functions, which are again 0 before time 1/2, and which then verifies a system of differential equations. Okay, so again, the system of differential equations is a bit obscure. But what we can do after proving this is just see that with analytical manipulation, see that the first coordinate of this couple must verify the differential equation of the previous theorem. Okay, so these are just manipulation of differential equation. So now our goal is just to prove this fluid limit result for this couple. So in this direction, we need to prove actually two things. The first thing is that we want something continuous in the limit. So we want to see that the jumps of the processes G and D are small. Okay, we want to see that their jumps vanishes in the limit. Okay, so for D, actually, this is easy. Since the number of discarded edges can only increase by 0 or 1 at each step. But for G, this is more difficult, and I will try to explain how we can do to deal with this. Okay, so this was the first point. And the second point is that we want a system of differential equations in the limit. So actually, what we want to prove is that the conditional expectations of the jump verifies the same system of differential equations. Okay, the conditional expectations of the jumps plays the role of the discrete derivative in some sense, and we want to see that they verifies the same differential equation system in the discrete settings. Okay, so where the function fg and fd are exactly the functions that are involved in this differential equation, in this system of differential equation. And once we will have this, we will just apply some general limit theorems for such processes. For example, there is the so-called differential equation method that was developed by Nicolas Vormald in the late 20th century. and which gives some fluid limits result if you have both these conditions. Okay, so again, the first thing is that we have seen that the jumps or the number of discarded edges are small, and actually we can directly also get the second discrete differential equation just by computing the conditional expectation of the number of discarded edges. Okay, so this is just the probability to discard an edge at time m. And so you have two possibilities to discard an edge. Either you connect two frozen vertices, which happen exactly with probability g times g minus 1 over n times n minus 1. Okay, you want to connect two frozen vertices, or you connect a frozen vertex with a non-frozen vertex, but you discard the edge with probability 1 minus. Okay, and this is exactly the function fd which appears in the differential equation system. So for the process D, we are actually done, and we want just to now try to do the same thing and to understand the behavior of the jumps of the process G.
But the fact that you get the same differential equation, is that expected or not? Did the two objects satisfy the same differential equation? Is that just a chance, or there's some deep meaning behind?
I mean, it's not chance since we.
Yeah, by construction of the.
Yeah, by construction of the system of
Yeah.
differential equations, so the thing we have done is to compute this conditional expectation and this one, and try to find the corresponding system.
Mm-hmm.
And so.
So you wanted them to have the same differential equation.
Yeah.
Why? So what's the probability they're different?
So it is quite common in this random graph model to have these fluid limit results. So we expected some differential equations in the limit. And so, yeah, the idea was really to try to find what the differential equations was going to look like. Okay. I'm not sure.
I see. And you needed them to be the, no, just my question was why you need them to be the same? Otherwise, you cannot go with the proof. Is that important for the proof that you have the same differential equation? I guess.
I'm not sure to understand really the question. Sorry.
Yeah.
Okay, so now our goal is to understand the behavior of the jumps of the number of frozen vertices. And here we are going to use the relation with uniform random forest and try to study this uniform random forest. Okay, because the observation is that in your frozen Erdős-Rényi graph, the number of frozen vertices only increases as some tree become frozen. Okay, so either you create a cycle in a tree, or a tree is attracted by vertices that are already frozen. Okay, so the idea is that if we want to understand how the process G jumps, we can try to understand what the forest part of the graph looks like. And the nice thing about the frozen Erdős-Rényi is that actually, after a nice conditioning, so if you condition with respect to the quantities G and D, actually the forest part of your graph is uniformly distributed over the set of unrouted, unordered, and labeled forests, which contain n minus G vertices and m minus G minus D edges. Okay, so we have a forest which is actually quite simple to understand since it is uniformly distributed. And so, for example, if we want to upper bound the size of the jumps for the process G, we can try to understand what is the size of the largest tree in a uniform random forest. And another consequence of this free forest property is that we can completely express the conditional probability of the jumps of the process G. Okay, so I just introduced a few notations. The notation V is for the number of vertices in the forest of your graph, and the notation E for the number of edges in this forest. And what we have is that we can compute the probability that the number of frozen vertices increase by K at time M. Okay, so we have one formula that I'm going to explain. So the last term is, imagine that you have a tree of size K in your forest. What is the probability that this tree freezes at time M? So either you create a cycle in this tree, or this tree is connected to a vertex which is frozen and the edge is kept. So this gives you the last term. Now, how many trees can you construct with V vertices? You have to choose the vertices involved in your tree. So this gives you V choose K. And then you can use what is called K-less formula to say that there is K to the K minus 2 trees of size K, possible trees of size K. And finally, what is the probability that one given tree of size K belongs to the forest? Since the forest is uniformly distributed, this is exactly this ratio of cardinalities of set of forest. Okay, and in the same vein, we can just compute the conditional expectation of the jumps of G just by summing this term over K. So this gives us a formula which is nice, but which is not that easy to understand because of this ratio of cardinality of set of rows, which is quite complicated at first sight. Okay, so because of this term and because of the free forest property, what we are going to try to study, and we are going to try to answer two questions. So the first one is, how can we estimate these quantities for any values of n and m? And the second one, to upper bound the jumps of the process G. So the second question is, what the asymptotic behavior of the largest tree in a uniform random forest? Okay, so we are going to try to answer both these questions, and actually the solution to these questions resides in one encoding of the sizes of the trees in a uniform random forest, thanks to some well-chosen random walk.
There's a question from online.
Yeah.
So just to make sure, uniform random forest on K vertices assigns the same probability to the forest on all K isolated vertices and a spanning tree on K vertex.
Can you repeat the question? Sorry?
Yeah, okay, maybe you can read from kills. Actually, Matteo, if you can just unmute yourself and ask. Okay, I'll ask him to unmute himself if he has a question.
So this was due to, so this is due to many researchers, and the first traces of this encoding date back to Colchin in the 80s. And then there was study of Butikov and Luchak and Pitel in the 80s and 90s. So how can we see this? The first thing is to try to count these forests. Okay, so how can we do this? We fix numbers n and m. So n will be the number of vertices in the forest, and m the number of edges. And maybe the easier way to count this forest is to add some indexation of the trees. So since you have n vertices and m edges in your forest, you have n minus m trees, which we are going to index. And so we want to count the number of such forests, which tree sequence sizes is given by any sequence ti, which verifies that their sum is equal to n. And this number is just this quantity. Okay, so first you have a multinomial factor which counts the number of ways to partition the set of vertices into n minus m trees of size ti. And then you make the product of ti to the ti minus 2 to say that for each tree you have ti to the ti minus 2 ways, different ways to construct a tree. And so if you just sum over all possible choices of sequence ti, and if you remove the indexation of the trees, what you get is this formula for the cardinality of the number of forests with n vertices and m edges. So we've got, when you sum over all possible values of ti, so we've got this formula, which is nice, but which is not that easy to study, actually. You can try to study it with combinatorial stuff. And actually, Rényi tried to do this in the 70s using generating functions and things like that. And he gets, for example, asymptotics for these cardinalities as n goes to infinity, but only for m fixed. Okay, so this is nice, but actually we want to have some more general results. And one way to do this is to have some probabilistic approach and to encode uniform forests with random walks.
Because here you want both m and n to be large.
Yeah, exactly. Okay, what I'm going to present right after is that you have a similar phase transition when m approaches n over 2 again. So we want exactly m and n to go to infinity simultaneously. Okay, so we can define for every x in this interval, we can define these probability measures, where tx is the exponential generating function of Cayley trees, and have this expression. And we can just define a random walk with jumps, which are given by the distribution mu of x, and which start at 0 at time 0. And we look at this random walk upon time n minus m, since the number of jumps of your random walk need to coincide with the number of trees in your forest. Okay, and we can simply try to compute that the probability that your random walk ends up at state n after n minus m jump. And to do this, we can simply sum over all trajectories, or over all sequences, such that their sum is equal to n, and make the product of the probability mu x evaluated in ti's. And just using the definition of the measures mu of x, we got this expression, which is actually proportional to the expression we got for the cardinalities of the set of forests. So what we add and what we can rewrite is that we have this relation between the number of forests with n vertices and m edges and the probability that this random walk ends up at state n after n minus m jumps. And
So this is to show the equivalence between the two countries.
yeah, exactly. And more generally, since we only consider the trajectory such that their sum ends up as state n, what we can say is that if you look at a uniform random forest with n vertices and m edges, actually the sizes of the trees in this uniform random forest has the same distribution as the jumps of this random walk, but conditioned on the event where the walk ends up at state n after n minus m jumps. And for example, the size of the largest tree in such forest has the same distribution as the largest jump of this conditioned random walk. Okay, so we, in some sense, we reduced the problem, which was a random graph model, to a problem of random walks, which is much more easier, and for which we have plenty of methods to study these random walks. And just to note, so this was true for every x in this interval, and just to see how can we study these measures. So if you take x in the open interval, what you have is measures with finite variance. And if you take x to be in the extreme case exponential -1, thanks to a scaling formula, you can compute the tail asymptotics of the measure mu of exponential -1. And in this case, you are in the domain of attraction of a 3-half stable distribution. Okay, but whatever, the idea is just to say that we reduce the problem to some random walk model. And so again, the idea is that for different values of n and n, the idea is to find the right value in some sense of the x to study and estimate these probabilities and the random walk by the use of local limit theorems. Okay. Actually, it can be a bit trickier sometimes because sometimes we will choose x, which will depend on n and m. And sometimes you cannot apply directly local limit theorems, but you can do a bit like in local limit theorems, so it's simplified your life tip. Okay, and thanks to this, and thanks to the study of this walk, we have results, phase transition results for the size of the largest tree in a uniform random forest, which is really similar to the result of Erdős-Rényi for the classical Erdős-Rényi model. So you have in the so-called subcritical region, you have that all trees are small and are of size log n with high probability. Then at criticality at time n/2, you have trees of size n to the 2/3. And finally, like in the classical Erdős-Rényi model, you have the emergence of a giant tree. And here you have the small difference with the Erdős-Rényi case. So in the Erdős-Rényi case, what we had is that the second largest component was of size log n in the supercritical regime. And here what you have is a second largest tree of size n to the 2/3. So this is a bit different, but the idea is that we have a similar phase transition for the three components in a uniform random forest. And we also have, again, thanks to the study of this conditioned random walk, we also have equivalents that I did not write, but we have estimates for the value of the number of forests with n vertices and m edges in the three same regimes that I wrote here, and it was due to Butikov in the 80s. Okay, so we are basically done with the three limit results we want to prove. So with these tools, what we want to prove, I remind you, is we want to prove a fluid limit result for the total number of frozen vertices in our frozen Erdős-Rényi random graph. And so we wanted to understand what is the behavior of the jump of this process G. The difficulty is that if we look at the critical point n/2, what we have is actually a critical forest. Okay, so this was part of the result of Contain-Curien in the critical regime. So this is not good for us because we have seen that critical forests have trees of size n to the 2/3. So this will be too large for us to get some fluid limit result. So what we need to do actually is to prove some technical results, which says that if you do not look at time 1/2, but at time 1/2 plus a small epsilon, what you have is a subcritical forest. Okay, so what we proved is that for every small epsilon, if you look at time 1/2 plus a small epsilon, the forest part of your graph is subcritical. That means that the ratio of the number of edges over its number of vertices in the forest is less than 1/2 minus a small positive constant. Okay, so this was really a technical part of our proof that I will not present today. And we can just say that we reduced the problem to prove that the number of frozen vertices is large enough right after the critical point. Okay, so this was this was quite technical, so I will not present it now. And we can just, with this fact, actually, we can just conclude the proof of the fluid limit. So first, what we know is that we have a subcritical forest. So the largest trees of this subcritical forest are going to be small, and we can use the results of Luchak and Pittel, or more precisely make some large deviation on this result to see, for example, that the probability that jump is greater than 1 to the 1/4 is exponentially small. Okay, so you only have small trees in your forest, and so the jumps of your process G are small. And for the conditional expectation, we can simply use the formula we had for the transition probabilities of the jumps of the process G by summing over K. And we can use the asymptotic results of Britikov to estimate these quantities, these cardinalities of set of forest. And after some AV calculations, what we get is this expression plus a small O of 1. And this expression is actually exactly the expression we wanted in the differential equation we presented before. So we can simply apply the differential equation method, so the general limit theorems for convergence of such process on every interval which looks like 1/2 plus a small epsilon plus infinity. And we've got our convergence result and our fluid limit for the quantities G and actually also for D. And just before concluding, one remark is that when you make the calculations for this sum, what you get is that the only remaining term which come from the second part, so from the part which come from the P times Gn, and the first part of this fraction has actually disappeared in the limit, which illustrates the fact that in the supercritical regime, the main contribution to the new frozen vertices actually come from the attraction of the vertices that are already frozen. Because since you only have small trees in your forest, it is really difficult to create a cycle in a tree and thus to create a new unicyclic component. Okay, so this is really the difference. So this is why we focused on the case P positive, and this is the difference with the case P is 0. So just to say a few remarks on the case when P is 0 before concluding. So what we add in the case when P is 0 is that the forest part of your graph is self-organized, since it has no interaction with the frozen part of your graph. Since the only way to freeze is to create a cycle in a tree, so you have no interaction if you with the frozen part of your graph. And as I mentioned before, when you reach the critical point n/2, actually the forest itself reaches some critical regime, in the sense that its number of vertex edges is close to the half of the number of vertices. Okay, and the idea is that since the forest is self-organized, it will tend to stay in this critical regime. Okay, so we have what we call a self-organized criticality phenomenon. Okay, so if you only look at the forest part of your graph, when you enter the critical, when you approach the critical regime, you have trees that are of size n to the 2/3. You just add edges, some trees are going to merge, and at one point you will create a cycle in a tree. But since you only, so if you only look at the forest part of your graph, it just disappears from the forest. But the fact is that since there is no interaction with the frozen part of the graph, the smallest components that are represented in the right here will not freeze. They first have to grow up a little bit, and I have to merge with other trees, but they will not freeze. Okay, so this is the main difference with the case when P is positive. When P is positive, you have a subcritical forest with small components that are attracted by the frozen part of your graph. Okay, and even if we have this self-organized criticality phenomenon, actually we believe that we can still get the fluid limit result for the number of frozen vertices, but just taking another way, which is, so before I presented you a fluid limit result for the number of trees of any given size, and I presented you it as a corollary of the fluid limit for the number of frozen vertices. And actually, in the case when P is 0, we believe that we can take the other direction by first get the convergence result for the number of trees of any given size. And we say that we can simply compute these conditional expectations, saying that a tree, the number of trees of size k increases by 1 if two trees of size I and j with I plus j equals to k merged one to each other. And it decreases by 1 if you connect a tree of size k with any other trees. So we've got this expression. And so our conjecture is that we can have a similar fluid limit result for the number of trees of any given size to the unique solution of this system of differential equation. And we also think that we can completely solve this system of differential equations and get the fluid limit result for the number of frozen vertices to some function which is actually, so again, which is a deterministic function, but which is actually much more simpler than in the case when P is positive. Okay, so we believe that we can get the same results, but in the opposite sense, in some sense. And we think that it will be actually a bit easier than what we have done in the case when P is positive. And just to conclude with a last application, and then I finish. a nice application, I think, of our fluid limit result is that we can completely, in the case when P is positive, we can completely understand the behavior of what we call the absorption time, which is the first time when all vertices are frozen in the graph. So this is the first time when actually the process stops. Okay, since once you have only frozen vertices, the process all the edges are discarded and the process stops. And so thanks to our fluid limit result, what we proved with Benedict is that this time is actually close to n log n over 2p. Okay, so if you consider the first time when all vertices are frozen, and you divide it by n and subtract log n over 2p, you get a convergence to some random variable. And this is actually related to the result of Erdős-Rényi, so the first time at which the Erdős-Rényi graph is connected, which is close to n log n over 2. Okay, so this is just a nice application of, I think, and which is not direct, and we have to work a bit to get this result, but this is a nice application, I think, and we completely determine the behavior of this first time when all vertices are frozen. Okay, so I think I'm just gonna stop now, and thank you for your attention.
Okay, so yes. Any question either from here or from Zoom?
Well, thank you, Vincent. Maybe I have a small question. In the case P equals 0, you said that the forest was not uniform. That's right?
No, actually the forest is
uniform. Okay.
Yeah.
But you still have to count the number of trees of given size.
So when P is 0,
nk is the number of trees of size k, right?
Yeah, exactly. So this is the number of trees of any given size.
Okay. And so if the forest is uniform, you obtain a relation between these nks, right?
Yeah, but actually for example, for computing these conditional expectations, we just use the frozen dynamics. So the frozen mechanism. Okay, so to compute this, actually, we do not need the uniform property of the frozen graph, the frozen forest part of the graph.
Okay, but it remains uniform. It's just that you don't use it. Okay.
It remains uniform. Yeah.
Thank you.
Let's use a question from there.
Nice. So V1, yeah, so thank you for the question. So in the case when, for example, in the Erdős-Rényi case, what you have in the limit is a Gumbel distribution. So with a double exponential cumulative distribution function. And here what we have is actually a Gumbel distribution plus some constant factor, if I remember well. So this really looks like the result of Erdős-Rényi when you just have a Gumbel distribution in the limit, but just with some factors that depend on the value of P. And but yeah, this is really just some distribution plus some corrections, if I remember well. So we can completely actually determine its distribution.
Okay.
Yeah. We have its complete distribution, and if I remember well, again, it depends actually on an integral of the fluid limit for the quantity for the number of frozen vertices. So yeah, it depends on P and on the fluid limit of the number of frozen vertices, but we can compute everything in this for this limit distribution. I just do not remember what appears exactly in the limit, but I know that we computed more or less everything.
Okay, if there are no other questions, let's thank Vincent again.